My name is Michael Els. I'm a data scientist at MaxPoint, and I'm going to talk about dynamic control for purchasing of online ads. That's kind of a difficult title to understand. And basically what I'm going to try and walk through is a project that I worked on last year, which is a fairly typical data science project. And it's basically how we control the speed of the ads that we buy online. What I'd like to kind of focus on in this talk is, I sort of say not math and not programming. I'm kind of lying a bit. There's going to be some of that in there. But I don't really want that to be the emphasis of it. It's kind of just to show that these solutions actually work for the problems that we care about. And that I'm not actually just lying or using some package that's got a whole bunch of magic going on in the background, that I can actually just really take like 3 lines of simple something and get it to work. And then I also want to focus on a couple of the methods that I use, which I feel are very underutilized. Things that I didn't necessarily cover in coursework at grad school. I was in a stats and econ programs. And I feel that they are very, very useful in data science, and I don't really see them being used very much, and I think they're pretty simple and effective. And then I also want to kind of showcase IPython notebooks a little bit. I kind of feel about programming languages the way I think most people feel about sports teams, and I very strongly prefer IPython and Python in general over things like R. But so just to put some context around the problem, I'd like to first take a couple of slides and just speak about what we do as a company. So we are programmatic advertising, computational advertising, which means we sort of try and build algorithms, much like high-frequency trading firms on Wall Street, to figure out what are the optimal ads to buy, what is the right price to pay for them. We try and bring in a whole bunch of external data sets. We build a bunch of our own data sets to figure out what extra information can we glean over our competitors to pick better ads for our customers. And so we work with big ad agencies. We work with clients directly. We don't build pretty pictures and creatives and give them a theme. They come to that with us, and then we're purely a machine learning shop. Like, we figure out, we're going to go find exact users on exact URLs online and put the most relevant ad in front of them. And the goal for us is to sort of maximize the ROI of our client, because the more that we can do that, the more money they throw at us, right? So they want to sell X number of products. They want to get a certain amount of traffic to their website. And then they have a bunch of people like us. They give us money. And who's ever getting them the best return, they give them more money. So that's kind of what we're doing. And so it's basically like a machine learning arms race between us and our competitors. And so the type of things that we care about is we built some sort of ad tech targeting platform. It's hyper-local. Is one of the main things that we do. Is we do a bunch of like geolocation models, amongst other things. We are both cookie and cookie-less solutions, which has been pretty effective for us as they've been slamming down on all the cookie policies, particularly in Europe. And then we do a bunch of stuff around crawling all the content and doing topic modeling and recommendation systems, and quite a variety of things. So just a brief overview of what I'm kind of talking about when I say this is sort of you're the user, you're all happy, you're browsing the internet, you go to your web page. It's going to then walk through step 1. It's going to go hit up the publishers like CNN.com, and then it's going to send you the content, step 2. But it's going to send like 3 empty boxes inside of that, right? There's going to be the banner ads that need to be there. And inside of that, it's going to actually send a link and says, hey, go call up some ad exchange, like Google or somebody that now basically brokers ads for CNN and other companies. Then Google contacts us, and everyone else is sitting on these exchanges, which is it's a clearinghouse, it's an auction. We have like 50 to 100 milliseconds to respond to any one of these. And then, so we have a bunch of code that sits on what we call bidders. They have to churn through like some information that we see very, very quickly and decide whether or not we're going to buy these ads. And if we want to buy these ads, how much do we want to pay for them? And then sort of that goes through step, we send a response if we want to buy it. And then it goes back to the user browser. The exchange sends to the user who won. And then they call us again, and we say, oh, OK, we won. Yes, here's an ad. Put this ad there. So the problem is that these exchanges send us like 12 to 15 billion ads a day. And we only want to buy like a couple 100 million or something. We want to buy a lot less than they're sending us. But we also want to buy the best ones. So we want to have some way to predict over time how much we should be buying at any given second or any given minute. And so that's sort of what where this project comes in, is how do we filter out in real time which one of those billion requests should I be buying at any given moment. So part of this is like we've got most of our other projects are around sort of like users, the media, the geography, the time, and there's some pricing stuff as well. So there's a very, very, very broad array of models that we run, and we try and come up with sort of some way to score every single one of these requests in basically real time, because we give ourselves 50 milliseconds. So everything has to run and score stuff in under 50 milliseconds, so that we can essentially score every single one of these 12 to 15 billion requests instantaneously and decide whether or not we want to buy them and whether or not and how much we want to pay for them. And so that's kind of where this problem comes in, and sort of the focus of like where we come from as data scientists in the company is obviously we care about machine learning. We want to find smart ways to do things. We want to find smart ways to do them automatically and at scale. So the typical process would be building lots of prototype examples and actually doing proof of concept. And then we try, if possible, to implement that in production. Or in this case, I had to hand it over to an engineer and walk through how we actually want to build this, because this needs to run in Java, and it needs to run on every single ad campaign in our company in under 1 second. As in every ad campaign in the company has to run this in that same second at the beginning of every minute. And I'll get into why that happens. And our typical process is, this is very much taken from an IPython notebook that I made last year that I actually took to engineering, and this is what I walked through. I built the whole simulation in IPython, and that's what this is. There is the full simulation embedded inside this presentation that I would go take and walk through them and explain, this is what we want to do, this is why I think we should do it, and this is why I think it works. So the background is what we internally call the pacing problem, is we want to know how do we want to pace an ad campaign. And for each ad campaign, we have some target number of ads that we want to serve every minute. And we'd like to serve the best quality ads at every opportunity. The problem is we don't know when the best ads are going to come for the day. It's pretty easy to look back, and I can look at yesterday, and I can say, oh, well, these were the best million ads. I should have bought those. But I don't know what's going to come up. It's highly variable. And I have to make some predictions about what I want to do. So yeah, and there's a few reasons why I want to do that. Part of it is to, our competition is they can sometimes flare up at different times. Everyone has their own way of doing this. And I also want to make sure that we don't end up in some situation where someone else comes in late in the day and they suddenly buy all the good ads, the good ads that I think are good ads and they also think are good ads, and then I can't deliver on my contract to serve X number of ads today. There's also some desire about smoothing your serving across the day. You can see it as hedging. Yeah. So this is the proportion of ads that we see. Well, this is the proportion of ad requests that we see by hour this is average over a week in the US. So ideally, we'd probably want our serving pattern for ads to look something like this. I would expect to serve pretty few ads around 5 in the morning because there are not a lot of people up on the internet then. And I would want to serve most of my ads sort of in the middle of the day and the evening where I see a lot of people like actually online doing things. Partly because if I want to serve lots of ads at 5 a.m., I'm going to have to kind of like dig down and buy a lot of relatively poor content, whereas I could get better quality ads later on in the day. And this curve is not fixed. We would change it. Sometimes we'll do things to learn which are optimal times of the day to sell certain products. We'll realize that we get much better engagement for certain things. It's sort of like if we're going to do something around selling sandwiches or whatever that people order online, there's really no point in me doing that at like 10 o'clock at night because they're not going to do that. People don't really want that then. You'll see massive spikes around lunchtime. So we'll probably want to load up the few hours before lunch and try and get in front of that sort of buying behavior so we can try and influence those choices. So one of the things I came up, so this is a little bit of math. It's much easier than it looks like. So this is a very nice little algorithm that I came across. Again, as a statistician, I never saw this ever, and no one in my team had ever seen a PID controller. And then I spoke to some people in the engineering department, like not computer science engineering, but like engineering. And like they were like, oh yeah, this is bread and butter. Everything runs with this. And it's basically like a feedback loop mechanism. So a side note, like where I came across this is I was building a drone. And I was doing one of those things. I did it the hard way, where I tried to do all the programming myself in Arduino. And I needed to figure out how do you keep it level. And so then they use these types of things that you pick the right voltage to go to each motor. And sort of you have this correction algorithm kind of does that. And so it seemed like a good idea, and we went and tried it out in the system. So this was all kind of like a hunch. We actually were building this new system, and we didn't know how we were going to control it. So this was part of why there was all this simulation and setup, because I had to prove it was going to work. The basic idea behind this is we sort of have some set point, some goal that we want to hit, and that would be that curve I showed earlier, where I have some goal, like every hour or every minute, I want to hit this target. So this is the target I want to hit. I have some process value, which is, this is just like the thing that I'm trying to measure. So for us, it's the number of ads that I've served in that minute. And so my error is the difference between the two, right? And I obviously want that to be 0. And then there are a few other terms, so these big K values, which is just, they're all just constants. It's nothing special. It's basically how much weight I should put to this term. So I'm going to go down to this equation down here. So essentially, I'm going to have some output UT, which is basically what would be equivalent to a throttle of a car. They use these in actually the self-driving cars, and pretty much any automated process that you want to control, flows of liquids through pipes, navigation. And so this is essentially, you can see it as like a throttle. I want more or less. And then you're saying you want to be a function of your error, but I'm going to take sort of like 3 different functions of my error. I want something proportional to just plain multiplied by my error, so that if my error is big, then I want to make a bigger change in that direction. If my error is small, I want a smaller change in that direction. Then I want some integral term as well, which means if I've been consistently wrong for a long time, I want to remember that, which means I should speed up, right? So if I've been wrong like 10 iterations, and I've been wrong 10 iterations in a row, then that middle term is going to get big. And whatever that ki is, multiplied by a number that's increasing, I'm going to get some acceleration in my correction. And then the third term is just a derivative component. I made some change in the last time period. And was that change, how big of an effect did that change have? If I actually made a big step in the right direction, then it's a pretty good idea that I should do that again. So it's literally just looking at my error 3 different ways and adding them up, and that is my throttle, right? So I'm going to speed up and slow things down. So it's pretty simple in concept. I do this kind of like cheating thing because I need to find these 3 parameters, and so it's kind of hard to find stuff in 3 dimensions. So I decide I'm going to go try and find it in 2 dimensions instead. So these guys, Ziegler and Nichols, came up with this transformation, which is basically a stable way of mapping this stuff from 2 dimensions to 3 dimensions. And that's all that is so that when I run some optimization algorithm on top of this, I can find good values slightly easier. But I'm literally just going to translate those back into those Ki, Kp, and Kd parameters. So it was a pretty useful thing. So this is very simple code. So I'm not actually doing anything fancy. I wanted to show this. I'm literally just making a PID class and assigning everything to just some value. And I have my update to the Ziegler-Nichols parameters. I read in my Ziegler-Nichols parameters. I set my Ki and Kd parameters. And then this is the exact few lines that we saw previously. Is my P contribution, the proportional contribution is just Kp times the error. The cumulative, I just do the integration, so I just keep adding up the error forever. Then my I contribution is just Ki times my cumulative error. And then the same with the timed error, the delta. I just work out a delta and multiply that. So it's not any rocket science going on there. So I make a toy example. And I kind of skipped over it earlier. I feel it's important to understand a lot of these things very well. I get it's very nice to take lots of packages and go and implement them and go, hey, it works. But when you're building something for a big production system, and I want to go, once I have a lot of faith in this, I can go grab something cool like the Azure machine learning stuff, and I can go plug it in. But until I've done that and I realize how it can go wrong and how I must really tune this, I really want to have a good understanding of what is going on with my method and what is going on with my data. So we had a good talk yesterday morning. I think one of the opening ones downstairs was about really understanding your data set and what your data looks like. And that's very much the first half of the problem. And I think a lot of people have really started grappling with that. But the second one is really understanding the model that you're going to use to solve a problem. And I encounter a lot of situations where I think people don't take the necessary time to really understand what the technique they're using is doing under the hood. Because then when things go wrong, like you don't know what to look for once it's gone wrong. And so that's when making these kind of things is pretty handy. So this was an example of just that thing running. So kind of gimmicky, I know, it's animated. So what I have here is I have some, that yellow sort of like step thing in the middle is some arbitrary set point that I made. And then the blue line is the process value. I want to get it to that point. I started at 0. It doesn't know how to get there. I've got my controller output, which is that UT, the throttle that I'm going to use. So I can essentially just move it up and down. It can go up in one dimension. And it literally just goes through. You saw the code. That was the exact PID class that it used. It literally just walked through and did that. So it would step through at each point and say, OK, well, you're far from there. You should go up. And as you can see, it kind of accelerates. And then as it gets there, it realizes it's getting there. And it starts to slow down. And then eventually it overshoots a bit, and it comes back down. And the nice thing about this is, well, I want to see what happens if I change that parameter. And then I get really ugly things. So if I'm serving ads, I don't want that to happen. That's right. And then I stopped. So yeah, and then it eventually decided to start again. So when you've done it like this, you can go open it up and you can go look at, well, which term was doing that? What was causing the misbehavior? And you can hopefully find nicer ways to do things. And you can sort of play with it and figure out what parameter space should this be? So what we did in reality was try to define some objective function to measure what a healthy system looked like, and then just left it on Python overnight with a lot of cores and said, go do a massive grid search and go tell me what a good bounding box is for these parameters. So that was kind of cool. That was nice to see. It sort of worked. It did something that looks like I want that to happen. It was pretty obvious that tuning is going to be important and that I should build in some safeguards. So one of the problems that comes in next is that the process that I'm measuring is not very smooth. So I had that very nice constant blue line that was a perfect function of my controller output. And in reality, doesn't look like that. So we would need to do some type of time series smoothing over this. And again, this is another sort of area I feel strongly about. Is I see a lot of stuff around is still ARIMA or something frequentist. I'm Bayesian. It's something that they tend to be slow changing. They've got a built-in lag. It's entirely backwards looking, or at least to some extent, you have to keep a chunk of previous data inside there to smooth it. And it's just some offline algorithm. What we really should be using is more dynamic linear models. And they're forward-looking. They're completely online. You just need to know the last state of things. And I get nice certainty estimates around my current state. I have a pretty good idea about what is going on. Are my measurements good right now, or has something actually fundamentally changed in the system at this moment? And which is a very different type of confidence interval than a frequentist model confidence interval gives you. And sort of on a side, on a footnote about that, is we found this incredibly useful when we do a lot of things and all of our data is streaming and all of it is over time. We actually, I back of the envelope, so it's not an accurate number, but I back of the envelope that we run about 3 billion DLMs a day at max point across our system. of which these pacing ones probably only account for 4 to 5 million. So again, we would update these at least once a minute for every campaign that we're running in the company. And so I go over because I've realized at least the circles I run in, that I think a lot of people aren't very familiar with what a dynamic linear model is. So this is the last little bit of math. But I want to go over a basic Kalman filter, which is the simplest version of a dynamic linear model. This is just, I'm going to smooth out some straight line. But you can really do this. It's like when they say dynamic linear model, they mean like any linear model you can follow over time and make work like this, which includes like basically anything that falls in the GLM framework you can do this with. And then you can get really, really good, accurate estimates that account for time properly, unlike many, many linear regression, ARIMA stuff, you can't add in covariates. And this is really the way that time series should be done. And it's what all high frequency traders, hedge funds use this exclusively to do all of their stock forecasting and things. So just very simply, it starts with I have some process X that I care about. So for us, it would be the number of ads I'm going to serve per minute is what I want. And it's going to be some function of whatever X was in the last period. And then there's some control equation. Maybe I know that things speed up or slow down at certain times. This was actually developed for physics applications. So they would know there would be some structure in the way things would change over time. But we're not going to have to care about that. And then what happens is there's the state X that I care about, the amount of ads I'm going to get. But then I don't actually know exactly that. What I do is I measure something. So I measure ZK, which is the number of ads that I actually sampled in a minute. Because again, my ad serving is very variable. So if I were to pick and buy like the same buying rules and leave it flat for like an hour, I would get like a completely different number of ads every minute. So what I actually need is the average of that. I want like a nice, smooth, real-time central average that I'm going to get. So we have some measurement ZK that we're getting. And so then we make some assumption that they're normal. They've got the noise, the measurement noise R, the process noise Q. We can give some structure onto all these things about how they change. Again, yeah, it's just one straight simple line. I'm looking at the previous input. So everything that's there is going to be all the A, the B, the H. It's all just one. Actually, B is going to be 0. I don't have a control equation. Then the next piece of interest is, so I kind of care about working out this covariance thing. So I can just define that I have sort of two phases to this algorithm. The one is I'm now sitting at a point where I haven't yet measured data, and I want to know where do I think my system is going to be at the next time point. That's not our problem. That's the stocks. That's high frequency traders' problem. They want to know where's the stock going to be in the next moment. What I care about is where is the stuff right now. So they care about the a priori estimate. I care about the a posteriori estimate. I want to know, I've just measured something, right? I've set a setting for my PID. I've told it that I want to go at this speed. And I want to know where was I actually, not the noisy measurement that I got in about how many ads I actually served. I want to know if I were to leave this constant now for the next half an hour, how many ads would I serve on average per minute? So I care about getting my a posteriori update. So we can define the errors as whatever the true value of X is minus my previous estimate. And we can update these. We can get some covariances. There's a bunch of math. Oh, I should have mentioned. All the notation comes from this paper at the bottom there by Welch and Bishop. It's a very good introductory paper for anyone that cares about Kalman filters. But one of the key takeaways here is why I put this in here is I wanted to get to this equation, which is called a blending factor, or sometimes just the gain or Kalman gain, which is trying to say how much do I trust the new measurement. So it has two essential inputs in here. So P is like kind of roughly an estimate of what Q was earlier on, my process noise. And then R is my measurement noise. So what it's saying is, if I have a lot of measurement noise, if I know that these measurements are very noisy and they could be all over the place, then this tells me how much I should believe a new measurement. So as R gets bigger, it means, well, whatever new measurement you get, trust it a lot less. But then P is also saying, because it's my process noise, so as my process noise gets less, it also says, well, trust your measurement less because I know my process is very stable. So it's kind of a nice way of internalizing at any given time point, how much should I trust the next bit of data that's going to come into my model? And so the whole thing can just be summarized in 5 lines, which translate exactly into 5 lines of code. And it is, I've got my time update step, which is I'm going to look at what I thought the state was going to be based on all the previous information, and I predicted it out. And I'm going to go and work out what my predicted variance is going to be. And then I'm going to actually get a new measurement. And I'm going to go work out my Kalman gain. How much do I trust this new measurement? And then I'm going to go update my state. So this is my a posteriori estimate of the state of my system. And I have the Kalman gain. Basically, how much do I trust this new ZK that I got in? And then I can update sort of the new variance on things. So it may seem like a lot of math, but I think it really boils down to a few inputs. And if you take the time to work through it, it makes a lot of sense, and a lot more sense than ARIMA. And this is all the code that it takes to implement a Kalman filter class. It's literally those 5 lines that were before there. I just institute all these self-contained values. I have my x a priori, which is just a times the x posteriori plus the control. And it's literally exactly the same as what was on the previous slide. And then I kind of make up an example now, another toy example, just show that this works. So what I'm going to do is at each time point, I'm going to draw n random uniform variables between 0 and 10. And I'm just going to count how many of those are above 5 and how many of them are not. So I should have some like noisier series bouncing around that's stationary. And it's again, so there's nothing going on. I've initialized everything just at some values that are roughly in the right place. I start my Kalman filter, and then I just make a data frame, a pandas data frame to collect everything. And then I want to actually run it and see what it looks like. And I get something like that. And then at some point, I change. So at iteration 50, I jumped up, and I was taking 20. I was going to, and I added an extra 10 trials. So what I want is a system that can lock on to 10 for the first half and to 15 for the second half pretty quickly. And if I had, again, some moving average-based model, it would have taken a long time. It would have needed almost all of the actual observations for its window period to have actually been in the new state for me to get an accurate estimate of the new state. This thing got there in about 5 iterations. And then again, like I have this nice toy example. I can sit and I can tweak these parameters. So what does it look like if I say, well, okay, my estimates are actually a lot less noisy than that, then they look more like that. What does this look like? And we can try it again, and we can go and see that it hugs the blue line a lot more closely and jumps up almost instantly because it's trusting its measurements a whole lot more. And then we can sit and tweak and get this to be exactly how we want it to be. So it's kind of important that for my PID algorithm, so again, this is nice. It kind of works. Again, tuning is important. And it's important because I don't actually want a smooth filter. I would have a problem if I had a flat line there, because I am actually getting variable estimates. And my PID controller is looking for something like, I made a change to my controller output, and I want to see a change in the system. If it doesn't see a change, then it thinks it's being ineffective, and it could get confused. Or it's going to try and make very big changes because it said this little change that I made didn't do anything. And so I don't want something too smooth, but I want something kind of smooth, at least something a lot less variable than what I'm measuring, but something that generally moves in the right direction whenever I've made a change. So then I put it together. So there should be nothing new here. I'm just showing you some of the code so that I'm not cheating. That's everything that I put in there. There's no, There's no bells and whistles around it. It's exactly the 5 lines that were the PID, and it's the 6 lines that was the Kalman filter. Like that is all that's being run, and then I'm just simulating data around it. So just initializing everything again, basically, I'm returning an empty data frame, a PID object, and a Kalman filter object. And then I'm going to actually run it. And the way I'm going to run it is the exact same thing. I've got this random uniform that I'm trying to pick how many of them are above 5. They're randomly between 0 and 10. Except this time I haven't fixed the number of trials. I've told it, this is my PID controller output. I want my PID system to tell me how many trials should I take if I want to hit my set point. So what was my set point was defined? Yeah, I start my set point at 5. It's just arbitrarily. And so for the first one, I want my PID to tell me that your controller output should be 10. And then just as I walk through it, I'm changing my set point to 8. I change it to 12. And then I change it back down to 4. And sort of as it's going through, right, I run through it. I get my process value, this random generated number. I go to my Kalman filter. I say, go update. Go take a step forward. Then I say, give me your X a posteriori estimate as my sort of smooth value. Work out my error. My error goes into my PID. My PID comes and tells me what I should change things by. And then that's it. And then I just collect all the data. And we can, again, walk through that. And so here is a system that now learns. With the red line is the value of the PID controller output. And then the blue and green lines are the same as before, where it's trying to learn what it should do at any given point. So it doesn't do that bad a job of getting at that. And again, I have all these things now in a nice little test framework, so I can go back and I can change any one of my parameters. I can see how reactive do I want my Kalman filter to be? How reactive do I want my PID to be? And I can sit and I can change these things, and I can see, well, at what point will they break? So maybe I want to change this to 5. And then I can rerun it and see how does it change. And there it badly overshoots and it's doing right. So that's clearly very undesirable. Again, part of this whole, I can now find some bounding box at where things would work nicely. And these are kind of slow and they're gimmicky. So I made static versions instead. Run, and we can just get the same stuff instantly. And so it kind of looks, that one does a better job of hugging the actual set point that I want to get. It seems like I want a more reactive PID. And so that's a pretty good proof of concept in my books. I was quite happy to get to that point. So it also all kind of works. Again, I'm back to the fact that it seems like tuning is kind of important. And the movements of the PID control output is not, okay, sorry, that's a separate point. But anyway, so that kind of works. But getting on to the next problem is, in reality, my PID movements, when I move down, like if I move my PID, my controller up like an extra 1 trial, I've got a 50% chance of getting another observation. In the ad world, when I add another like URL, I could add like, one of the sub pages of like my mom's blog, and then I have like a 1 in 5 chance of getting an ad in a day there. Or I could have added a URL from YouTube, at which point I'm going to be getting 100 ads every second. So when I take one of these steps with my PID, there's a very variable chance of the amount of ads I'm going to get. So I don't actually have, this is a very nice like clinical, like pharmaceutical trial basically that I've built here that doesn't really represent what the ugly world looks like. So I know this and I need to prepare for it. So this is the distribution of ads for the top 100 websites in the United States. So it goes down very quickly. And I did the 100 because if I go to like 1,000 or anything more, then you actually can't see these lines. They just like hug the axis and they're gone. So this just gives you an idea of how skewed the distribution is for sort of sampling a volume of ads. So one of the things that I do to get around this, and sort of how we try and to automatically tune these PIDs, great, because they're all different. Every ad campaign is different. One ad campaign maybe wants to serve, they're like a small mom and shop business, and they want to serve 1,000 ads a day, and just to like the area around their shop. Someone else might be like a Walmart or a Target, and they want to serve like 50 million ads or 100 million ads in a day, and they want it to be all across the country, and they've got all sorts of things it needs to hit and meet. And as we saw with the tuning for both the Kalman filter and the PID, it was very, very specific to sort of the numbers it was getting in, the magnitude of the ads that it was dealing with, on sort of how responsive it should be. And so the fact that I don't want to sit there for thousands of ad campaigns every day and like go and do a bunch of tests and figure out, well, what should the parameters be for this one? What should they be over here? Also, we have a production system, and everyone else it's all kind of new. The Exchange is also all kind of new. Everyone has problems, and Exchange will shut down for an hour, and then I've lost a third of my volume, or we have some system bug, or we pause things for a release, or just lots of things happen and stuff turn on and off all over the place. We actually can't afford to have like a static setting on any one of these algorithms. So we need to figure out how can we have them teach themselves how should they tune themselves. So I kind of lean on something called particle swarm optimization, which is a fairly simple idea. So you essentially have a lot of solutions. So you create this population called a swarm, where you sort of, and in this case, it would be the KU and PU parameters of my PID, because these are my solutions to my tuning. All the parameters on my Kalman filter. So I create a whole bunch of them, like in a space that I think, well, these are all possible. And then I take a step forward, and I have some objective function. And I say, well, how did you all do? Which one of these particles did the best? Which looked like in the space was the best spot? And then you kind of look at that, evaluate it, and then you move all those particles like a little bit closer towards it, a little bit closer towards it. But at the same time, you also add like a random bit of noise so that they don't all end up at one point. And the idea is you have this fuzzy learning system that's always like kind of around an optimal point, and they'll always be looking around that space as you iterate through things. Yeah, so that's roughly what it does. Problem is, we can't do that because there's no way I can design a nice objective function for this system. And I also can't see if I had one other PID algorithm, I don't know. And I can go and work out what it would have done at the previous step, but I don't know how many ads I would have won at the previous step, because again, it could have added some different set of URLs into my list to buy that had very different volume like behind them than the one I actually chose. So I don't have a good way to do that. So I kind of, again, whenever I can't do good pure stats things, I cheat. And I created what I call a naive particle swarm optimization, which is, again, because I've got to start the system, and I don't know where to start the system. So I pick what we've discovered were very sort of basic, safe tuning parameters. I start the PID at like serve no ads. I start my Kalman filter at you are getting no ads. And I pick some values that will start adjusting slowly, so like very low KU and PUs that aren't gonna adjust quickly to some point. And then I pick a couple of new particles around there. I don't pick a whole lot because, again, this all needs to run for every single ad campaign in the company in the same second every minute. So I can't have thousands of particles that I can store and move across time for every one of these ad campaigns. So I just pick like a couple. In this case, I make 4 new ones. I sort of take my KU and my PU, and I move each one up a little bit and down a little bit, and that cross product gives me four trial PIDs that are very close to the one I'm using, but not the same. And then, again, the problem is I can't validate retroactively. So I rather just look at, well, how much was I over or under by my serving? And which one moved me the most in the correct direction? And then that's the one I'll pick next. And then I update my particle, and then I move forward with my new PID at whatever the optimal parameters were, and then I do it again at every step. So again, maybe that sounds kind of complicated, super simple. All that I do, that bit of code, just go take and make a new PID K-, I copy my initial PID, I just reduce the KU a little bit. The other one, I increase it a little bit, decrease PU a little bit, increase PU a little bit. And then I look at those. Like, again, there's nothing fancy. You'll see I have a PU floor and a PU ceiling, and a KU floor and a KU ceiling. I've got a bounding box, right? Because I'm going to move these things around now, and the computer's going to do it, not me. I need to tell it what's the safe space to play in, right? I know if I make KU like 100, bad things are going to happen. So I've given it this, like, you're only allowed to stay inside. Yeah, you can go, fluff around and bounce wherever you want to go, but that's the box. I know in our system, nothing good happens outside of this box. So then I can, again, take some real data. So I pulled this data from a real campaign. So this was like a few hours worth. This is the actual distribution of scores of stuff we did serve. So I'm going back to the high frequency trading world, and I'm doing some back testing. I can't generate true new data, but I can at least go back to data that we do have and pretend like I'm going to go over it again for values that I do know. So it's pretty skewed. There are a couple of bumps here, right? So this is essentially the score range here. This is the range that my PID controller has to move around, right? So at 0, it's maxed out. It can't buy more ads than that. At above 9, there are no ads to buy. So, and it has to choose at any given time where it wants to be on the spectrum. So I can kind of see that it's going to walk down here, and it's going to get its first bit of volume over there. And if that's not enough, it's going to actually hit like this dry patch. It's going to get nothing. And it has to keep walking down until it gets a little bit there. And then at some point, it's going to hit over here, and it's going to get a whole lot, or at least a whole lot relative to what it was getting. And it's going to have to deal with these types of fluctuations. And then it's going to get back here, and it's going to get extreme, especially to this point where I get like an absolute ton over there, and then basically nothing. For some reason, there's a big dry patch, and then it shoots back up again. So I needed to realize when I must take big steps and when I must take small steps. So all inside these simple tuning parameters, and it needs to go figure that out. And again, over time, this is, if I were to plot that same data across time instead of by score, this is how the stuff is coming in. So highly variable, all over the place. And I need to kind of smooth that out. So at the end of the day, this is what it looked like. Again, I made some arbitrary set points. And it could move itself around and do a pretty good job. So my first set point that it was trying to hit was actually well above what it was able to hit. So it did the right thing of starting at serving no ads and bottoming all the way out to say, OK, well, this is all I can do. This is everything. This is buy everything. And then eventually, I actually get the volume that I can actually satisfy my volume. And then it says, well, OK, well, now I don't have to buy everything. So now I can only start buying the best ads. And so then it starts to raise its threshold. And then again, yeah, suddenly something turned on and a whole lot of volume became available. Maybe an exchange came back online. And suddenly, well, oh, yes, well, now I can stop buying all this bad, worthless stuff at the bottom. And I can actually buy, really good things now. And then at this point, I said, well, actually, now I only want to buy a few ads. And so it can, again, just instantly raise itself up and become very, very selective. And then the next plot is just, this is an example of the KU and the PU parameters of how it's moving them around. And so sort of in the beginning, where it's way off, it realizes, well, actually, these need to become pretty responsive. So let me sort of drop these immediately and raise this up so that I become responsive. And then it kind of hit this like happy spot at the middle where it didn't really do too much moving. It had that bump there where it had to like jump up a little bit. But it was pretty happy. But then over here, right, I suddenly said, well, I want to serve little ads now. And you need to go adjust a whole lot. So it then realized, OK, well, I need to make some significant changes now and become much more responsive to things. And so it moved itself to a whole other space. And it kept it there, right? It kept it there because this is of sort of like a different order of magnitude, the number of ads that I want to serve at a given minute. So it doesn't need to keep some stable KU parameters. Maybe the stable parameters for that volume is at these higher KU and PU parameters. And then when I raised it up again later on, it sort of went back and stabled down. So I never did any math to go and prove that any of the stuff converged. Like, that's what PhDs are for, and I'm not into that. So what I did anecdotally notice that stuff did tend to always converge to like certain stable points, because I went through a lot of these. And they would almost always find like some very happy point, and then they'd stay there. So that at least gave me a lot of comfort. And then just, again, back to the way we should be building algorithms, I think, as data scientists, is to really understand like what they're doing. Like often when I pick a lot of packages up in Python, I'm a big fan of using packages, and I use them all the time. But to really understand what's going on inside of them, again, so that I can know when something goes wrong, what does it look like when it goes wrong? When it goes, if it's going wrong, what should I look at? What can I do to fix that, right? Because I've got to go and build in these safeguards. Like when you're actually running this on a scale in production and it's going to change itself and tune itself, people can't look at it. And we need to figure out what are the safeguards that I build in this algorithm. Because when you read a stats paper or an engineering paper and they describe to you how you use this, great. But the guys that built the algorithms didn't tell you at all like how to constrain them into doing something that your business wants. So an example of this is the sort of like, we had some issue with our servers running slowly. So occasionally that they would need to do like a vacuum on the disk or something would happen, and then everything would kind of be slow. And we didn't want to build in like our true time delta because I knew I was running at a set interval, so I would just tell it this is the interval you're running at. And then when this happened, it would sometimes take like 2 or 3 minutes to run. And then I was like, oh, well, why are all the campaigns slowing down, right? Because what happens is it's now collecting 3 minutes of ad impressions that we served, but I'm telling it you only ran for 1 minute. And it says, well, okay, well, then you served way too many ads for 1 minute, slow down. And so then it would slow down. And then it said, okay, well, what did you do now? Like, oh, well, you still collected way too many ads, keep slowing down. And then we actually had something chronic go wrong with the box that ran that. And then you kind of get the CEO walk over to you one afternoon and say, why is the system grinding to a halt? And I'm like, what do you mean? And he's like, well, you just built the new pacing algorithm. And so you go look at it and you're like, oh. And then we very, very quickly undid that. And again, so raising and lowering these threshold values, these controller outputs, they're not symmetric business decisions, right? So what I mean by that is we built some safeguards around how fast I'm willing to raise and lower that controller output. Because if I were to lower it down like really like far too quickly, and I were to grab like all of YouTube, then we'd finish serving that campaign in 2 seconds. And that would, a client would be very unhappy. They wouldn't pay us. They'd cancel us. We'd lose business. Bad things happen. So moving down is not the same as moving up. If I'm going too fast and I want to move all the way back to the top, it's not a problem. I can make up for that in the next 10 seconds. So those are two very, very different decisions. And we essentially have basically for us like a different loss function in how we would want to move up versus move down. And so again, another type of like business rule and logic that we would want to build on top of an algorithm. As well as, as the same as starting carefully. Like don't start all aggressively to rush to the right point. If you're running an ad campaign for a month and you're going to be running all day long, you don't need to get there in 5 minutes. You can get to your ideal point in like half an hour or an hour. I mean, no one's going to know. No client gets hourly reporting or minute-based reporting. So we can start stuff pretty carefully. And then again, also just build in some checks for bad behavior. Like we can run these simulations. Like we can build in and like ways to detect fingerprints of what does a bad algorithm look like. Like it's easy to build in checks. Like when is my PID oscillating all over the place? Like when it's doing that, it should be really easy to detect. And it can send me some kind of alert. We have alerting systems built throughout the company. They can give us some feedback and say, hey, there's a problem right here. Or it can even pause the campaign and say, you should deal with this. And then similarly, we have very good internal monitoring systems. We have some account management team that sit and monitor all the ad campaigns and talk to the clients, and sort of they get very nice sort of real-time charts that kind of look like that. So this is just a screenshot from our actual portal view of what an ad campaign looks like running on the PID, which is, again, all the same colors. The red line is the actual controller output, what we call the PID pacing threshold, and how it moves around. And you can kind of see it. It hits somewhere, yeah, there's something big, right? It keeps like going down a little bit, and then it hits something big, and then it jumps back up again, and then we lose it. And that's the right behavior. That's exactly what I wanted to do. I wanted to sort of, it only needs to hit this green line is my target. And if it can't hit that with everything above, some high volume website, then I wanted to just, for a few seconds, touch the high volume website, get a bunch of ads there, and then bounce back up again. And so that's what it's going to do. It's going to keep like bouncing down, hitting that, going back up. And thus I get to sample like pretty effectively, the best scored ads that I want for this campaign across the day. I also picked this that actually has a good example of where something went wrong. It was turned off for a while. Something happened there. It was reset. It started back at 10. It knew nothing, right? So my measured impressions was 0. My threshold went all the way back up to the top. And then it slowly works its way back down, right, to find out where it should be. Hits something too big, goes, oh, okay, that was too big. And then instantly hits back to its straight line and carries on serving happily. So we actually do use this in production. These were all the core concepts are inside there. Those were the lines of code that I showed you. The only thing we added to those lines were business rules. Those core algorithms were literally contained in total 10 lines of code, 10 lines of Python code. It was actually implemented in Java again because it needs to run fast, but this is the type of working example that we'd go through with engineering, and they went and built it. And that's what it looks like. That's what our account managers look at on a daily basis too, if they're worried about something not working right. And, yeah, thank you for your time. And sort of part of the pitch is we are number 9 on Deloitte's Fast 500, fastest 500 growing tech companies in the US last year, which means we are hiring across the board. Thank you. Yeah. This is IPython Notebook. Yes, everything is in an IPython Notebook. And you can get what's called Reveal.js, which enables like a slideshow mode for it. You can use, you can either make them in HTML, or you can actually run the slideshow directly inside of IPython. I did that so that I could actually run the code in the presentation, which is because I wanted to sit and play with things and show you how stuff changed. And then on top of that, there was also, I was running a bokeh server, which is another great thing that Continuum was showing earlier, that would do all the streaming plots. Yeah. They would certainly use a form of a dynamic linear model. I don't know. Again, so the Kalman filter just has no covariates in it. So they definitely. I have a friend that works in that, and so he uses that. That's all. He exclusively uses that. So yeah. Yeah. I'm not using a particle filter. I'm using particle swarm.
Particle swarm to track
Right. I actually wasn't using it on my Kalman filter. I was just using it on my PID tuning parameters. Yeah. We could have, but yeah.
Because I was wondering if you tried.
Oh, yes. I did not, no. Okay. This was just like super easy and light.
Yeah, this sounds like very.
It was, right. So I needed something to run really, really fast.
Sure.
But yeah, no, so again, back to the dynamic linear models have a lot better ways of learning their parameters. They can all change over time. You can give them structures. They can learn. They can learn patterns over time. They can. You can add any covariates you want to it. They're very, very flexible. You can have all your covariances changed by time. It can observe every one of its parameters and learn what it should be. So it's a very, very flexible model. But I also wanted to show that you didn't need to go that complicated. It works pretty damn well without it. But, right. Great. Oh, sorry, yeah. Yes, we do a bunch of random forest stuff. Not with this, though. Well, I want a control loop system, right? So I want something that tells me at each iteration, it's what did you do in the previous state? What should you have done? How do you want to change things going forward? I'm not sure if right. I'm not sure if I. Yeah, the way I've been using random forest has just been over like a non-time based data set. It's just yeah. 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 No, that's good. Thank you. Sure. Oh. All right. Yeah. I don't know. My guess would be, and again, because I'm biased against R, is that they're trying to help you, so they're lying to you, and they're giving you something better that you should have actually asked for but didn't ask for. All right. All right. Cool. Thank you.